Okay, good morning and welcome to everybody. Thanks for taking time to come this morning and hope we can share some information here today, things that we're learning, things that we're seeing, and things that you can take back and use on your operation to make us all better. So look forward to the day of sharing and learning together. We'll do some introductions here before we get started or go too far. This is my family. You'll see some of us around here today. My wife, Hannah, here. Marissa's in the back. We'll go through our team. Ted and Miranda. Ted's here right now. I'm guessing Miranda will be here at lunch. Trent Strom is one of our newer sales guys here based in Hiawatha. Seth Miller helps us with the estimating. He's doing the audio here today. Cortland Byer in the back does a lot of our research and development, does a lot with water quality. So if you got any questions regarding, we're going to touch a little bit today on water quality and bicarbonates, some of the water issues, but that's kind of Cortland's area of expertise that he's working on. Since Carlos is coming down the stairs here, we'll introduce him. Carlos is our automation guy. So he's the controller, IT, electronics. He's an electrical engineer. So super sharp guy, glad to have him on our team. Joel Chesser in the back, probably a lot of you know him, one of our main guys out in the field and a little bit in the office. Logan Metzger is not here. Most of these guys are out in the field here, but Logan Metzger, Anthony Kale, Jake, Jared, Laban, Tyler, and then Leo, Edgar, Josue, Marcelo, and Alexis. So our team is growing. We've got a lot of really good help. Which we're thankful for. We couldn't do it without them. And then on top of that, we've got our outside sales guys and service guys. Trevor is here from Nebraska, lives in Hastings, covers the Nebraska area for us. Chris Wietrich is at another field day in Illinois today. We've got another full-time guy, lives just north of Peoria. Wyatt Byer lives in northwest Iowa by Rock Rapids. Taylor Zeltwinger is in West Central Minnesota. Then Travis and Brandon Wetstein, Travis Roki and Brandon are here back in they're somewhere. Travis will be presenting later this afternoon down by Joplin, Missouri, and then Brad Roki in northwest Indiana. So that kind of makes up our team. We're looking for help. So if you know of anybody that's looking for full or part-time or seasonal, we usually bring on a half a dozen or a dozen summer help. So even high school or college kids, we're always recruiting and looking for help and more team members. So business has been good. We're experiencing some growing pains and definitely looking for more help. And then we've got to figure out how to get everybody trained. So also use a couple subcontractors, Alliance Excavating out of Sabetha and Wisman Enterprises out of Milford, Nebraska. Help us quite a bit with installation and some subcontractors that do a lot of work for us. The NetFM team, that's a couple guys here with us. Tim Wolf will be presenting here in a little bit, is an agronomist with NetFM. Jason Scheibel is the NetFM rep for Kansas and Nebraska. And then Jim Ed Beach was not able to be with us, but he covers the rest of the states that we work in pretty much. So Iowa, Minnesota, Missouri, and Illinois, and the Dakotas. Most of you, at least those of you that are here, are familiar with where we're at, but for those of you that are online, just quickly cover. So we're in northeast Kansas, just across the Nebraska state line. We cover our farm. We actually farm here with my brothers, Galen and Glenn, and mainly corn and soybeans, a little bit of organic, doing some alfalfa, and have been playing with some grass seed as well. So kind of do some different things here. A lot of food grade corn that we raise for national starch down in Kansas City. Grimm's Gardens is our retail business and landscaping company, and that's kind of how we started and a little bit of our backstory. Back in 1993, we started growing blueberries here. So just south of the farm, we have 3 acres, or started with 3 acres of blueberries. We're down to about 1 acre now. Then we got into hydroponic tomatoes in the mid 90s. And that was really some of the early ideas that got us into drip irrigation. Then back in 2012, after the drought of 2012, we had a 40-acre piece just north of here, a couple miles, that we couldn't put a pivot on. A pivot wouldn't fit, and so we started looking at other irrigation options, and we were looking for a way to diversify our landscape company. And so that first 40-acre project was a joint venture between my brother Keith, who has the pivot dealership, and the landscape company. And once we put that first drip system in, the light bulb just kind of went off that here's a delivery system that mimics what I could do in the greenhouse. In the greenhouse, I would take a tissue sample of tomatoes every week, and then I would adjust what I was putting through the fertilizer based on what that tissue sample came back as. And so that was kind of how we got into this. We saw the opportunity, and it's just kind of grown from there. We used to irrigate with hard hose traveling guns. We put the first pivot up in this area back in 1997. In this area, all of the water is surface water. We drill a well, we're lucky to get 10 gallon a minute in this area. So we've developed ponds and reservoirs where we can catch the excess runoff water that we usually get. So our oldest system that we have here is right at 10 years old this year. There's some systems we take care of in Nebraska. We have one that's 38 years old and it's still running. We put a new filter on it this year, but it's still working the way it was designed. So that's always one question we get is how long can I get how much life can I get out of my drip system? And we typically say 25 years, but it all goes back to water quality, which is why water quality is a really big part of what we do, and why we're spending a lot of resources on trying to figure out how to economically make sure a drip system doesn't plug up. If a drip system were to ever fail, it would be because it plugged. And so that's why we need to really think about water quality and how we can make sure that the drip system stays clean. This is just a quick map of where all of our outside sales guys are, where we have people at, and this is where we've installed drip projects. So you can see quite a bit of concentration up and down Interstate 29. We don't have all the pins in Nebraska because some of them are stacked on top of each other, but we're well over 10,000 acres of drip in the ground since 2013. So it's a growing business, and we're excited about what the future looks like. A couple things I wanted just to share as we think about, especially as I look at who's here today. Most of you have a drip system or some kind of irrigation system, and I want to think about like the big picture, like as you think about what's possible, and what do we need to think about like going forward. Okay, and maybe you've got your first system or second system and you're looking ahead. This is kind of where we're at, and we've been irrigating since 1997. But we saw the value in water, right? Like water is key, and this land around here, 170 to 180 bushel APH would be pretty average for us, 170, 180 bushel corn. And with irrigation, with drip irrigation, we're probably at 270 to 280 is kind of where we're at right now. We feel like there's more potential, but right now we're sitting in that 270 to 280. So for us, it's 100 bushel almost every year. And so we're looking at how can we get water to more fields? That's always our challenge in this area. So this is a project that we took on, or it's part of the pivot company, the drip company, our farm, and one of our neighbors. And so this is a pipeline project that we installed. So this blue line is a buried line. We're sitting right here, and we've got approximately 5.5 miles of pipe buried, and we're filling reservoirs all along the way. So there's a reservoir here. We've got a reservoir right here that's tied into it. There's a reservoir that's not even on the map that's right in here. We've got another one right here. I think there's 7 or 8 reservoirs that we fill during the off season, and then we can transfer water between all of these points. And all total, when this project is done, it'll irrigate about 2,000 acres. So 10, 20 years ago, I would have, it's just to get you thinking out of the box, like what's possible, what can I do? And when you start thinking about big picture and long term, this is a dryland area. 20, 30 years ago, there was no irrigation here. And now we're looking at what can we do on our own farms in combination with some neighbors to move water, hold water, store water. And in a year like this, even this year, which is, we've had good rain up until about 2 weeks ago. It still is going to add a nice return on investment. So as you think about irrigation, just kind of to think the big picture. Sometimes we think, well, this one little field and this one project, but start thinking long term, what you can do on a larger scale. Especially if you have land in a combined area, how you can share that water, how you can work with neighbors, how you can build a reservoir where you can maybe hold water if you don't have good well water. So just some thoughts to throw out there. I'm going to throw a few maps up of some projects we've done here in the last year or two, just kind of to show, what guys are doing. So this is a project up in Iowa, just north of Fort Dodge. This is a 700-acre field. So we've, 5 years ago, the average size drip field for us was probably 40 to 80 acres. I think our average drip field now is probably 120 to 160 acres. But here's a 600-acre project. We're pulling water out of the Des Moines River, got a permit there, and then we've also got a well that sits right here by these old grain bins. So drip irrigation isn't just for small scale, odd shaped fields. This grower had looked at putting pivots on here, and out of the 700 acres, the pivots were only going to be able to hit about 480 acres, and it was going to take 6 of them. And at the end of the day, the cost per acre was pretty similar. And so thinking long term and larger scale is something that I think we need to present, that we're not just small scale on small fields. We're starting to use drip irrigation on larger projects. This is a really sandy soil, had a lot of rock. It was kind of a challenging installation, but at the end of the day, this is going to make it a really high productive farmland in Iowa. This is another project that Travis did down by Joplin, Missouri. I think we're at about 550 acres. So there was a phase 1 that we did about 220 acres. And then we added another 330 acres down on the south side. So all feeding out of one well. It sits right here. They've got about 1,000 gallon a minute when they start the season, at least, pulling out of here. And then we're covering all 600 acres. Now, one thing that we have to think about on a project of that scale where they have limited water, that's one thing we'll discuss a little bit later, is how much water do you need? We have to look at crop rotations, especially this year. Down by Joplin, Missouri, these guys did not get rain, and he had more corn than he should have had for this size of this many acres. So thinking about crop rotation, how much water does my soil need, and how much water is the crop using is a discussion we need to always have at the top of our mind when we're thinking about larger projects and more water and how much water does it really take. Still doing a lot of work with manure. This is something we feel is a really great opportunity. We've got a couple guys here today. If you have questions, Abram Frank is here from Iowa, Todd Roque from just over by Sabetha. Both of them are doing manure through drip and seeing some good things. Abram especially, we've got some data from this year where he saw some really strong improvement on tissue samples from late season manure going through the drip. So it's something that we feel like there's a huge market. We're still perfecting some of the separation processes and how we can clean manure up to get it clean enough to go through drip, but it's definitely a growth market for us. Most of the work we're doing right now is on dairies in Minnesota, so we're working with a large dairy producer up there. I didn't update this number for this season, but as of this spring, we had already applied 80 million gallons of it's actually a feed pad runoff, which is not truly manure. It's all the runoff from the buildings and the silage piles and all the stuff. They can't let it go in the ditch because it's too dirty, but they have to apply it somehow. And so we're putting it through the drip system and saving them. It's about a 1.5 year payback for them right now. So we feel like there's a lot of opportunity with the SDIE and what we can do with in-season manure application. Injecting that under the ground where there's no smell, there's no runoff. There's a lot of benefits on that side of things. One of the pieces of equipment that I'll point out that's making that possible. So there's really 2 pieces of equipment we're using. Back up. Okay, so this is a screw press, which is a pretty common piece of equipment that basically takes out the big particles in the manure. And then we're going through a secondary process, which is this shaker. It's a super simple machine. This is only 2 horsepower, and it's basically like a big flour sifter. And it just sits there and shakes, and it removes, the solids come out the side, and the liquids drop down through it. And when it comes out the bottom, it looks like coffee. So it's a dark water, still has all the nitrogen in it. The potassium is still in it. About 30 to 40% of the phosphorus has been removed. So it makes a really usable fertilizer that guys can run through their drip irrigation. And then we're taking and blending that with water, so it's not 100% manure that we're running through, we're blending it with water. We've got several projects where we're looking at working with municipalities. So there's a lot of municipalities that store their water in lagoons and are discharging that at different times of the year. They'll discharge it down a creek. And the EPA is starting to regulate how much they can discharge. And so they're looking for ways to get rid of that water. And so we've got several projects on the drawing board right now where we'll be looking at taking municipal wastewater and thinking about what we can do to help these municipalities in combination with some farms and be able to get rid of their excess water. We just finished a project down in Holton, Kansas, at a hog processing facility for that exact same purpose. Currently they discharge their water into the creek, and it goes down the river, and the next town drinks it. But it's clean when it goes out. They do a great job of treating it. But long term, they're seeing the handwriting on the wall that that's not going to last very long. So just a side note, 5 years ago, I went to Israel, and I just went through my slides and presented them to our Sunday school class here a few weeks ago. And it reminded me that in Israel, 100% of their wastewater goes to irrigation. They wouldn't think of discharging their wastewater into a creek, because wastewater is fresh water. And the only other option Israel has for water is to desalinate something coming out of the Mediterranean Sea. They only get like 3 inches of rain a year. So they're taking all of the wastewater in Israel, gets treated, goes into an underground aquifer that's contained. So they've identified some areas where they can basically inject the water into the ground, so it's not on top of the ground and evaporating. And then they have wet wells that pull that back out of the ground, and then they distribute that to the whole country. So Israel's an amazing case study when you look at what we should be doing with water, especially in areas that don't have enough water. It's something that I think is an underutilized resource that right now it's just going down the ditch. And then the farmers get blamed for high phosphorus in the Gulf and high nitrates. Every single municipality is dumping their water in the river, and it's going to the Gulf. So I think there's some win-wins that we can talk about and some potentials out there, especially if you have farms located close to a municipality. It's something that should be talked about. And another interesting note, I read a book after I went to Israel. If the wastewater from the city of Los Angeles was all combined into a river, it would be the 7th largest river in the United States. Like it's phenomenal how much water we dump out of wastewater. Okay, I'm going to shift gears here a little bit, talk about some other new things that we're doing that we're excited about and think have some real potential. This is a project we're working on this year with a company. It's called NutraSense. They're based in Italy or Spain, based in Spain. So there's a few language barriers there, but we're working through that. And what it is a sensor that goes in the ground. I think I've got a picture of it here. The sensor is not much to look at. So I don't have a picture of it. It's basically just a little probe that goes in the ground, very similar to a moisture sensor. But what it's doing is it's measuring nitrate and potassium real time. So a lot of you are used to looking at soil moisture probes. You know what a soil moisture graph looks like. And we'll look at some of those here in a little bit. But this is going to give us every 15 minutes how much nitrogen and how much potassium is in the soil. Now, the question is, what do we do with that? Like, this is all of a sudden new data that we really don't know how to use. And so we're having to learn, what does that look like and what should it look like? But a couple comments about that is the soil makes a huge difference, because soil, especially clay soils, hang on to those nutrients. So if you have a high CEC value or high cation exchange capacity, you hold a lot more nutrients on that soil particle. And so what this sensor is measuring, it's not only measuring the leachable part, the part that's in the water solution, but it's also measuring what's on the soil particle that should be plant available. So it's an interesting project. I think there's 3 of these projects in the United States this year. I think we're the only one on commodity crops or corn, soybeans. Most of them are being done, or the other 2 I think are being done in tree crops and nut crops. So we're hoping to learn a lot from that. This is just a couple things, a couple interesting things that we've learned from it. So this is the actual graph from about the 6th of June until today. The top 2 lines here are potassium. So this is our potassium sensor, this is potassium, and these 2 here are nitrate. And they're just electronic value. They're not part per million, they're not pounds per acre. So you have to correlate what this means back to something that's actually actionable. But one thing that we definitely see is that nitrate has gone up and potassium has gone down. In other words, and we've got some more data that I'll show here in a little bit, we're applying too much nitrogen and not enough potassium. That's one of the key takeaways that we've learned so far, is that we are over applying nitrogen and we're under applying potassium. That's just a real quick summary of what we've learned. Probably one of the real fits for the nitrogen sensor on this is areas that are concerned about nitrogen leaching. So especially those of you guys in Nebraska that are starting to have nitrogen NRDs that are looking at nitrogen and groundwater leaching, we think there's going to be a big potential for this technology to eliminate or to be able to measure how much nitrogen is actually in that soil profile and how much is leaching. We have 2 different depths. So we have a sensor at 8 inches and a sensor at 24 inches. So we can see what's in that root zone and then what's down kind of below that root zone, or in other words, what we're losing out the bottom. And we lose nitrogen out the bottom. This is in a heavy clay soil. And so if you had a lighter soil, I think the CEC on this farm is like 28. So if you had a lighter soil, maybe a 10 or 15, which you see a lot of in Nebraska, you would be losing exponentially more nitrogen out the bottom. So just it's new. It's not something that we may have it available next year. We may want another year to learn before we fully introduce it. In addition to what we're doing with the actual sensor, so I'm just going to kind of go through the whole process of what we do. This is what's called a suction lysimeter. So this PVC pipe goes down in the ground. We have them set at 12 inches, I believe, and 24 inches. And once a week, we go out and we put a vacuum on that PVC pipe, and the bottom of that PVC pipe has a permeable stone on it, essentially. And so you put a vacuum on there, and over the next 24 hours, it sucks the water into that PVC pipe. Okay, so then we go out with a syringe and a piece of hose, we stick it down in there, and we suck that water out. Okay, so now we've extracted from the soil the water that the plant is drinking. Then we take tissue. We take the actual corn leaves, we put them into a garlic press, and we squeeze the juice out of the corn leaf. Okay, then we have these little handheld sensors, which this is, again, part of this whole project and part of our learning process. These sensors have been available. We've never known how to use them. But this company in Spain is kind of teaching us. But basically, it's a little pen sensor like we would test pH and EC with. And we can test potassium, nitrate, calcium, and sodium. And we can get a real-time reading of the sap and of that water that we sucked out of the soil. So it kind of makes us rethink like what's possible. Right now we take tissue samples. Like that's our standard practice. We take a tissue sample once a week, we send it to a lab, and we try to get some sense of the trend, what's going on in the field. Now we have a tool where essentially every day, if we wanted to, we could go out and take a reading from the field and get these 4 nutrients. And I'll cover this a little bit later. But these three nutrients right here, potassium, nitrate, and calcium, are probably the three of the key nutrients that we're focusing on. And we've known potassium for a long time. Kelly's going to talk about it after lunch. Potassium in particular is something that we underapply. We don't have enough of it. But now we have a tool that we can measure it every day. And so how do we use that? How do we use that data to help us understand what's going on in the plant? They're about $400 a piece, roughly, I think. Is that right, Cortland? Roughly $400. Yeah, right in that ballpark. So $1,600 gets you all four of them. So it's really not. I mean, you think about how many dollars worth of nitrogen you put out this year, right? Like I think we could pay for some of these things in a hurry by cutting back on some of our rates. So now, if you start thinking about looking back at that graph where we've over applied nitrogen, the nitrogen has trended up through the year, and we can measure that through either the suction lysimeter or through the tissue. I think we could start cutting back on some of those rates. And if you pay attention to what's going on in Europe right now, Europe is being clamped down on how much nitrogen they can apply. And so that's where this technology is really starting to take off from the standpoint of being nutrient efficient and not leaching nitrogen. So if you want to look at what's going to happen in the United States, probably look at what's happening in Europe now, and that's where we're headed. And so if we can get in front of that with some of these tools, I think we could be a lot more efficient. Plus, we could be ahead of some environmental regulations that could be coming. Okay, going to jump into some of the newer things we're doing with tissue samples. So that was kind of the summary of what we're doing with these. This is, if you've heard of SAP analysis, this is SAP analysis, but it's real-time SAP analysis. So in the past, SAP analysis has always been pull a tissue sample, put it in a cooler, and send it to the Netherlands. And a week later, you get data back. And our experience is we could never figure out how to read that data. Like there was so much information in there that we struggled to get actionable items out of SAP analysis. So this is what we feel like will be the next stage of SAP analysis, or more of an in-field SAP analysis that we can actually do something with. We're not getting all the nutrients. It's only these four, but we think this gives us a pretty good picture, especially when you look at potassium, nitrate, and calcium. I will point out this is only nitrate. It's not the ammonium portion. So if you're into tissue sampling or SAP analysis, NO3 is the only part that this sensor is picking up. It's not picking up NO4 or any of the other parts of nitrogen, which nitrogen has multiple pieces to it. Okay, so a little more information about tissue sampling and kind of where we're at with tissues. We're doing a lot of work with Next Level Ag in South Dakota. They have, I feel like Jason Schley with Next Level Ag is probably at the top of people who understand tissue samples and what to do with them. And so we've partnered with them, got a couple projects going on with them where we're trying to really dig into tissue sampling and learn more than we've known in the past. I think in the past, we've looked at individual values, we've looked at trends, we've started to look at balance, and Jason is probably pushing the balance and the relationship between the different nutrients. That's where he really focuses a lot of his energy, is what is that balance and which one do we need to be pulling the trigger on. So this is their newest dashboard, or their tool that they're using. A couple things that I'll point out that we're going to talk a little bit about is this cation to anion ratio. So if we look at cations versus anions, in order for a cation to go in the plant, it has to have an anion to go with it, and vice versa. They travel together. It's a positive and a negative charge, and you need both of them. And one of the problems that I think we've ran into is we've just applied nitrogen, right? We want our nitrogen number higher. Well, you know what? That doesn't work because it's only one side of the equation. And so if we over apply nitrogen, you actually block the other side of that. You actually go backwards. And so we need to start thinking about that balance, and just applying more nitrogen is not always the answer. There is a point that we need to maintain nitrogen at, but it's not the full picture. And so what does that balance look like, and how do we dig into that? So this is one of the balance tools that is pretty easy, or it's easier to understand. So if we look at this, this is basically saying that in this case, the nitrogen to potassium ratio, so we got N at the top here, we got potassium at the bottom, we actually need a little more nitrogen in relationship to what our potassium is. We have on the sulfur side, we need more sulfur. We have enough, the nitrogen to sulfur ratio is off. So if we look at this, our phosphorus to sulfur is off, our nitrogen to sulfur is off, so sulfur is definitely a limiting nutrient. It's a nutrient we're probably going to see a response from. So I could have put a 2-hour presentation together on what we've learned by looking at this, that we'll probably do for our winter meeting. But just know that the relationship between the different nutrients it's key. It's not just the individual values. So this is one of the ways we're looking at that. So this is, again, different tissue samples. We've got some corn and soybeans in here. And we've got the anions totaled up and the cations totaled up. And then we're looking at this ratio. And the ideal ratio is a 1. So we want a 1-to-1 ratio between cations and anions. And really, we're only looking at 3 cations and 3 anions. We're pulling nitrogen, phosphorus, and sulfur. Those are our anions. The cations are the potassium, magnesium, and calcium. So if you look at the ratio between those and you add those numbers up, what does that relationship look like? Later in the season, it's much harder to hold a proper ratio, especially on soybeans. Corn, early in the season, it seems like it's not as hard, but definitely you can start seeing some trends. Right here, this sample, we're at a 0.78 at R2, 0.63 on soybeans at R2. So definitely we're starting to see some imbalances, and a lot of that comes from potassium and calcium. So now if you go back to what we're seeing on the sap, again, we can look at potassium and calcium real time, every day. And now we're seeing in the tissue that those are the 2 cations they're throwing the equation off, right? They're the 2 nutrients that are throwing things off when we look at that cation-anion ratio. So, key takeaways: too much nitrogen. I think that's, I don't know, I don't want to say that's a blanket statement, but 90% of the producers we're working with have too much nitrogen, especially too much nitrogen early. One of Jason's kind of key points is he doesn't want to see more than 45 part per million in the soil at any given time. So in other words, that's about 90 pounds. And if we're over that, we're over applying nitrogen. There's too much, and it's throwing everything else out of whack. The other thing it does, it burns up carbon, which Kelly and Mike can talk more about after lunch. They're focusing a lot on that. Not enough potassium. So that's a general statement, and we've known that potassium is a nutrient that we've always struggled with on tissue samples. But as we're looking at these new sampling methods with the sensors and the SAP and the suction probes, we do not have enough potassium available. Calcium. This is one that really came on the radar last year because of bicarbonates, which I think I've got that slide next. Let me just go to that quick. I'll have to bounce around here a little bit. This is where we really started looking at calcium, and this is one of Jason's soil samples where we're looking at not only the total pool of calcium in the soil, but also the H3A value. So H3A is the Haney extraction, and it's the actual plant available calcium that's in the soil. So on a standard soil sample, you would have probably seen this ammonium acetate extraction, and you would have seen a value on this particular sample of 2,997 pounds per acre, or excuse me, part per million of calcium in the soil. If we look at the H3A extraction, this one here, we've got 433 pounds available, or part per million, excuse me, and 337 part per million. This is an area where it's actually one of our pivot irrigated fields where we noticed that under the pivot on an ideal rainfall year, we had corn under the pivot yielded 29 bushel less than the dryland corner. And so we started asking questions and we started digging into why would that be. And what we learned, which I'll share here in a little bit, is it came back to the bicarbonates, and bicarbonates are tying up calcium. And so all of a sudden we don't have enough available calcium in the soil, which now we know that we're seeing that on the tissues, and we're also seeing that in the sap. So calcium is one of the nutrients that we have not, we've always said there's enough in our soil, and there is, but it's not available to the plants. And so calcium is one of the nutrients that we need to start addressing in season. We're looking at calcium chloride. We've got some tests going on with that right now, where we can take, it's a dry product. You can melt it in water very easily. This is what you use to melt ice off your sidewalk. So calcium chloride is fairly readily available, but it has a lot of chloride in it. We're trying to understand what is that going to do? How much can we put out? But the calcium part of it is readily available, and there's other forms of calcium that we can apply as well. Melting urea. So I just want to talk a little bit about as we look at how do we get more nitrogen in the right form. I think that's another thing that I'm not going to spend a lot of time on it, but it's not just putting 28 and 32% out. There are different forms of nitrogen, and we need both of them. We need nitrate and we need ammonium. And when we just put out 28 and 32%, we're only putting out nitrate. And if we could get forms of ammonia out there, the plant is going to be 20 to 30% more efficient if we can put ammonia out. So how do we put ammonia out? You can melt AMS. Urea has a portion of that in there, and it's a more balanced form of nitrogen that the plant can use. So we did a little bit of testing with that this year. You can take dry urea, just like you would spread across the field. We took 800 pounds of dry urea, put it in 1,000 gallons of water, agitated it, and injected it through the drip system. So it's very easy to melt urea. Most elevators don't carry that, but it's a pretty simple process that most guys can do on their farm. If a guy had a seed tender, you could set up a conveyor, that dumps urea in, or a tote or something where you could auger that in or meter that in. So melting urea is something that I think we need to be looking at as far as a nitrogen source. Melting potassium. So taking 0062, most potassium that you buy is going to be an 0060. It's a prill. 0062 is a powder, and it melts in water much easier than 0060, and it's a little cleaner. Not everybody carries it, so finding it can be a bit of a challenge. But melting that that potassium down is again a pretty simple process. It's really cost effective. It's not going to cost you any more per pound typically than 0060. It's just a matter of finding it. So you can ask Kelly some questions about that this afternoon as well, or over lunch, because he's done a lot of work with melting potassium down. So urea, potassium, and chloride or calcium are things that I think across the board we're seeing as nutrients that we need to be addressing differently than we have been in the past. Okay, we'll talk a little bit about water quality. I'm just going to touch briefly on this. Probably most of you have seen some of this, and it's more of a recap, but I want to hit on it because it's still a really big deal. So I'll just kind of go through the high points and what we've learned and what we're seeing. There's two minerals that can plug up a drip system quicker than anything, and it's iron and manganese. So every sample, those are always the first two that we're going to look at, iron and manganese. If we're over a 0.5 part per million on iron or about 0.2 part per million on manganese, they need to be addressed. If they're over 1 part per million, then we have to get more aggressive. And if you have both of them together, that can be even more difficult to work with. So just understand that these are the two that we've always known were an issue, but we're starting to spend more time focusing on them because they are starting to pop up in more areas. And the other thing that we've seen change is that wells aren't consistent. My brother Glenn's got a well that when we first put it in, I think it was 0.2 part per million iron. Today it's 2 part per million iron. So it's a 10x increase from the day it was drilled until 3 years later. So started out, system ran fine. Now we're starting to see some plugging because we didn't address it from the get-go. So understanding what your water quality, what's in your water as far as iron and manganese, are really, really important. And again, that's kind of Cortland's expertise, but it's something we can help you with. But understand that these two are kind of the two ones that we have to worry about most with plugging. The next one we're going to look at is bicarbonates. And this is the one that I'll say it's the underaddressed part of the water that is clear. You can't see it, but it's there. And it causes an incredible amount of imbalances in the soil as you apply nutrients. So just to kind of throw some numbers out to understand what that means. So if we have a 495 part per million bicarbonates, which I would say most samples are between 3 and 500 that we're seeing. So everybody's got, I shouldn't say everybody, most people have between 3 and 500 part per million bicarbonates in their water. What that does is it ties up cations, okay? So bicarbonates are an anion. They tie up cations. So again, back to chemistry school, cations and anions, they balance each other out. So if you have, let's say 400 part per million bicarbonates, they tie up 1,100 pounds per acre of cations. 1,100 pounds per acre for every acre foot of water. So if you apply 12 inches of irrigation water to your field, you have tied up 1,100 pounds per acre of calcium, potassium, magnesium. Two of those, calcium and potassium, are ones we just said we're having all kinds of issues getting them high enough. Here's why. Because we have bicarbonates in the water that are one charge, and they're tying up the other side of that equation. Okay. Again, this applies to drip. It applies to pivot. We're seeing it on all of our irrigation here on our farm, and we're surface water. We always thought that surface water wasn't as big of a problem as well water, but turns out our surface water has high bicarbonates in it. And so 20 years later, we're seeing what's underneath that circle yielding less than what's outside the circle when we have enough rainfall. Here's why: because we've created an imbalance in the soil, and now we've got things that aren't working the way they're supposed to anymore. So it is treatable. Sulfuric acid or a sulfur burner are the two kind of go-to things that we're using right now. There's some guys in Idaho that are doing some things with some other types of acid that we're still learning about, but right now the two solutions we have are sulfur burners or sulfuric acid. Let me just go to a test that I think I have on here that shows. So this is a sulfur burner. It basically takes dry sulfur. It has a firebox in it, and it melts that sulfur prill, takes the gas off the fire, injects it in the water, and it treats it, lowers the pH. It basically makes sulfuric acid. It's a very, very simple process, but it's essentially making sulfuric acid on your farm. Oh, too far. Okay, so this is a water treatment. Before it ran through the sulfur burner, we had an 8.6 pH. We had a bicarbonate of 306. This is after it went through the sulfur burner. We lowered the pH of the water down to 6, and we have 14 part per million bicarbonate. So this is a before and after of the same water, just what happened when it went through the sulfur burner. You can see sodium stayed the same. A lot of things stay the same. We don't affect hardness, but we knock out that bicarbonate. And what happens to it is it turns into carbon dioxide. So it gasses off, is where it goes. So it basically, there's a reaction chamber or a reaction venturi on the sulfur burner, creates this chemical reaction and knocks this bicarbonate out of here. So doing more and more work with those. The sulfur burners have proven to be a little bit of a, I don't know if I want to say they're a maintenance headache, but they're another piece of equipment. And so we're struggling a little bit with whether that's something that if a guy had 10 sulfur burners on his farm, he'd have a full-time job just keeping the sulfur burners running. So we're trying to work on some of the automation of that, how to make them simpler to operate. Sulfuric acid does the same thing, but the operating cost is about 4 to 5 times what it is for a sulfur burner. So you can do the same thing with sulfuric acid, but your operating cost per acre is going to be substantially higher. Just to this is just a snapshot of our database of water samples. Here's the bicarbonate column here, and I have them sorted based on bicarbonate level. So here we're all the way to 980 part per million bicarbonate. And on this particular spreadsheet, the lowest one I have is 430. Now there are additional samples below that. We've got some water down by Joplin, Missouri that's 150 part per million. I think that might be our lowest, is 150 part per million bicarbonate. So this bicarbonate thing is real. It needs to be part of your long-term plan. It's not something that's probably going to show up in the first year or 2 or 5 years, but as you get 10 and 15 and 20 years down the road with an irrigation system, this is going to start causing problems in your soil chemistry if it's not addressed. One of the ways they address it in California, so a lot of what we do, we look at how they're addressing things in California, is they're spreading dry gypsum on the soil. So basically the sulfur in gypsum will kind of do a similar process. So that's another treatment method. The sulfur burner is cheaper than spreading dry gypsum. So we've kind of looked at some of those operating costs and what does it cost to address it. But gypsum is another option for treating bicarbonates. Wanted to spend just a little bit of time talking about water usage, especially a year like this. I think we've seen, especially as we move south of here, guys that are drier, we've struggled to, I don't know if I want to use the word understand, but I think we need to do some more education on how much water is your plant actually using. And then we need to balance that with what you can apply based on your well capacity. And so this is just a quick chart that looks at corn water usage. This particular graph, it went from May 10th to October 7th. And you can see the different growth stages. Here's V12, here's tassel, silking, and we're starting to dent. These numbers over here, so this is crop water use, how many inches per day. And kind of the number that we've always used is a 1/4 inch per day. So you can see if we drew a line right here on a 1/4 inch per day, it would catch 70% of the season. We've still got this usage up in here that is actually higher than a 1/4 inch per day. Okay, so this is how much water that corn plant is using every single day. And if we use a 1/4 inch per day, understand that the days that we're using 4/10 of an inch, when it's 95 degrees and the humidity is 20% and the wind's blowing at 30 miles an hour, that plant can actually use a 1/2 inch every single day. That usage just goes through the roof. So what we need to, the other part of that equation then is what's in your soil, right? Like how much does your soil hold? And this graph right here does a really good job of showing different soil types and how much water they hold. And what these numbers mean, so we've got wilting point is kind of this bottom hash right here. Okay, so this is the point at which the plant starts to go under stress. This top line is field capacity. That's the point at which the plant is happy. There's no water standing in the field, but we're at kind of that ideal moisture level. So when we're irrigating, we're trying to stay inside that band. We want to be between these two lines right here. And if you look at these different soil types, on sand, we've got a total of 3.7 inches of water per foot. This is a per foot number, or excuse me, inches. Yeah, inches per foot. How many inches of water does that soil hold for every foot? And then you got to look at what's your effective root zone. Where's the roots of that corn plant or that soybean plant at? Typically, they're in that top 12 inches. We get later in the season, they might be down in that, they should be into that 2 foot range. But essentially, we can only use, for comfort level, we should probably only figure on that top foot. So if we've got 3.7 inches in that soil, and we're using 4/10 of an inch a day, or a 1/4 inch a day, or 3/10 of an inch a day, we need to start looking at what's that accumulative effect of pulling that water down. And what I want to, the picture I want to plant in your mind is, and because this is how I've started to think about it, it's like my checking account balance, right? I've got, let's say, $1,000, and every day I've got a withdrawal going on. And let's say, for easy math, let's just say every day I'm taking out $40. I'm taking out 4/10 of an inch. Eventually I'm going to go negative, right? If my irrigation system can only put in 1/4 inch a day, or maybe I've only got 1/10 of an inch a day, when do I go negative? And so those are things that I think we just need to think about when we're thinking about irrigation and water capacity and how much water that plant is using. Now, if we go over here into a silty clay soil, we've got 4.4 inches. You know what? I didn't say this right. These are not, you don't add these up. So 3.7 is not correct. There's 1.1 inches in the soil when we're at wilting point. There's still an inch of water in that foot of dirt. At field capacity, there's 2 inches in that dirt. Okay, so we only have 1 inch of water in a sandy soil. So, Roger, you've got some parts of your field down there. There's only 1 inch of water in that top foot, right? Guys down by Garnett, you're going to be down at this 2 inches of soil, 2 inches of water in your top foot, right? So everybody's got different soil types, different water holding capacities, but understanding how much water is in that soil. So sandy soil, we're holding 1 inch. Clay loam, we're holding just under 2 inches, 1.8 inches. Not a lot. There's not a lot of reservoir there, right? And which is why when we get dry for 10 days, things go backwards in a hurry. So just think about that reservoir that's in your soil and how much water it can hold and how deep are those roots and what's that reservoir look like and what do we got to do to keep it full. Soil moisture probes, probably the best tool to give you a snapshot into what that looks like. And this is one of the probably the best ones we're using right now is Centec. They do a really good job of showing where's that wilting point. That's that bottom line. And this is field capacity. This is that top line. So in other words, where are we at in being able to maintain that moisture level? The other thing that Centec has done is this is the daily gain or loss of water in the soil. So if you look at this bar graph right here, this is 0.2 inches. So if we drew a line across here, we lost 1/4 inch of water here. We've got some days that we lost 6/10 of an inch of water in the soil. So in other words, they're trying to calculate based on the movement on that soil probe, how much water did that plant actually extract from the soil? And they're saying that we're losing up to over a 1/2 inch on certain days of water is coming out of that soil. On the flip side, you can see a rain event here. So you can see we gained almost 1.9 inches. So there was a lot of room for water in that soil, and we had a rain event that soaked in nicely. If most moisture probes would only show you this bottom graph, and you see this big spike, and you see that had a big increase in the amount of water in the soil. This one here is actually quantifying how much water soaked in. Get a 3-inch rain, how much of it actually went in the soil. So this is the Centec dashboard. They do a really nice job of showing those changes. This is just a quick spreadsheet. It's very basic where I just went in and I put in how much water, and I was using 2 feet of soil. So I said I started with 2 inches in my soil, and these are the ET values. So ET stands for evapotranspiration. It's how much water theoretically that plant is going to extract from the soil. And so you can see we've got an ET value of 1,500, 2/10, 1/10 of an inch. It changes every day based on humidity and temperature. And so these are theoretical values of how much it's extracting. So if we've got a sandy soil, by the time we get to day 10, we're going negative. On a loam soil, we've still got 2 inches of buffer. And so as you think about your fields and your soil types, and you've got one part of the field that's a heavy loam and you've got another part that's a light sand, what is that management going to look like, and how are you going to manage based on those different soil types? One of the questions we get a lot is, well, how do I manage for variable soil types? And the answer is the ET on all of that field is the same. In other words, the corn plant that was in the sand, he's using the same amount of water as that corn plant that's on that heavy loam or that heavy clay. And so if we water just the amount that that plant is using every day, we're never going to overwater the sand, and we're never going to underwater the clay. So we don't necessarily need to set it up and zone it based on soil type. We've done some playing with that, but really what we need to think about is, what is that plant using, and how do I replace that every single day? If I do that, I'm going to have an even balance in my checking account. It's going to stay consistent throughout the season. A couple tools that we're working with. There's some new ones. This is one that NetFM is working on, where basically it's going to calculate your ET for your field every single day. So you would log into this dashboard, and it would give you, this is a field just north of here, our first drip field. We've got this tool we're testing this year, and basically today it's saying we're going to use 1/1400ths of an inch. Tomorrow 1/1500ths of an inch. So for the week we're using an inch of water. So just a good snapshot that's showing us how much water we're using. They're also trying to calculate how much rain we're getting and how much irrigation water we need to be applying. So giving us some recommendations based on that. This rainfall amount is it's not an actual rain gauge in the field. So that's one of the challenges is getting this value right when you're using a tool like this. Soil moisture probes, again, are still going to be the ground truthing of what's actually going on in the field. I'll just make a comment about moisture probes. As a company, we struggle to deploy moisture probes in a timely manner. Some of you know that. Long term, we want to move towards a permanent moisture probe system, a probe that's in the ground, it stays in the ground, and it gives us a reading 12 months out of the year. So we've got a few of them. Actually, Glenn's got one on his field we've had in now for a year. It's working really well. The probe has to be within 100 feet of the edge of the field. So there's some limitations because of wire distances, that if we put a radio, let's say at the edge of the field, we bury a wire and we have a probe that's permanently in the ground, we get a measurement all the time. And so that's the direction we want to move. The downside to that is we have to put the top of the probe below tillage. So we have that first sensor is probably going to be at 8 or 10 inches. In other words, we're going to lose the data of 0 to 8 inches. So as you think about the pros and the cons, we feel like that's a better trade-off than not getting a probe data until the 1st of July. So I think that's something we're going to be looking at, and we're trying to figure out how to deploy those and get them set up to where they're going to last for 10 or 20 or 30 years, where you have a sensor in the field that gives you data 12 months out of the year. Just a quick snapshot of some of the newer tools we're using for automation. This is a new dashboard that we've got from a company called Galcon that we're working with, that has what we feel like is a super robust and reliable controller that we're starting to use. So a few of you have seen some of these this year on some new projects, but basically it's giving us, this particular field has 3 different wells or 3 different irrigation fields, and we can see what's going on with all of these flows and pressures remotely. We can see pressure in, pressure out. So this, again, on a drip system, this is everything for knowing if your drip system is working right, is what are these flows and pressures doing. Travis is going to talk more in depth about this after lunch, and we talk about operation and maintenance. Again, same dashboard or same tool, we're able to quickly graph what those pressures have done over time. So this is a 3-day look at the pressures. So you can see that we've got filter flushes going on here. That's what these big dips are. The pressures drop when we flush filters, and then the pressure differential, or the spread between the high and the low side, widens a little bit. This one isn't as pronounced as some, but if you just a quick snapshot of what we can learn by looking at pressure over time. So with that, that's kind of my overview of what's new, some of the new things we're working on, things we're excited about. One thing I didn't mention that along with the manure side of things, one of the things that's driven us to is to make a more bulletproof connection system. for where we go from the PVC pipe to the riser. So if you've got drip, you know that one of the weak points is that where we put that barb and grommet in, that it usually happens in the first year or two, we'll have some of those pop out. Well, when we're working with manure, those guys don't want any manure leaking, especially the dairies in Minnesota. The sensitivity in Minnesota for leaks is incredible. So we've developed a system now where we are fusing. We're using high density polyethylene or a black poly line, and we're fusing that riser into the pipe. We're not using any PVC. There's no PVC on the whole project. So we're doing some new things with riser connections to make that better. Just a lot of because of the sensitivity of the manure, we're starting to rethink how we're doing things, and coming up with some better systems that we're pretty excited about going forward. So any questions for me? I'll be around.